Welcome back, grade 11s. We are here on another live show of Mindset Learn Extra, doing physical sciences here with Smithy, aka Megs. And we have another favorite physical science teacher, another Tracy. So Tracy, please tell us what we're doing today.
Well, today we're going to do diffraction. So we got fun things, and I'm going to be making use of you just now. I'm just saying that's just important.
Okay.
But we're looking at diffraction, why we see funny, you know, like when you're driving and you look through the car window and all the lights are hazy.
Yeah, weird.
Yeah, we're going to discuss why that is.
Okay.
It's actually very cool.
That's interesting.
Yeah, it's very cool.
That's awesome. Can I send you just quickly to the board so I can just tell them anything that they need to know?
Okay.
Okay. So, mindsetters, I hope that you tuned into the grade 10 show, but if you didn't, it's cool. I'll just tell you everything you need to know now. There's a new competition here at the Mindset Studios. It's got to do with future stars. So if you think you are South Africa's new future star, please go onto our website. It's www.mindset.co.za/learn extra with an X. And we're going to be here answering all your questions. I promise I'll answer and try to get Tracy to help me answer all your questions on Facebook. And in case you don't know the Facebook page, it's facebook.com/learn extra with an X. Or hit me up on Twitter @learn extra. But let's get into diffraction, because I know Tracy is so eager to tell you all about it, because I'm actually really interested to hear what she has to say. So let's go.
Okay, you can come back. Anyway, so we are going to deal with diffraction today. Okay. And what are we going to look at in today's lesson, guys? Well, we're going to talk about interference, which is something you did last year in grade 10. Very briefly, you looked at interference of waves. We are going to define and explain Huygens principle, which has many ways of pronouncing, but we're just going to pretend I'm doing it correctly. And then I'm going to demonstrate, hopefully with the help of Megan, and explain the diffraction of light waves. It's actually quite an important section. And this is quite a nice section for you grade 11s, because if you've got friends who are in grade 12, they're probably roundabout doing this section now as well, but they have to do calculations because they're still doing the NCS. Okay? Whereas for you, this is all very qualitative. And what we mean by that is this is all going to be explanation type stuff. Okay? So you need to be able to explain what's going on. All right. Now, let's just jump straight in and talk about interference, which is something you actually experience all the time without actually really thinking about what you mean. So if you think about, for example, you're watching television and your cell phone goes off, or you have it on silent, but you hear that funny noise, and sometimes you can hear it in speakers, and you go, oh, my cell phone's interfering. That's exactly what it's doing. It's actually why we can't have our cell phones on in the studio, because it'll interfere with the broadcast, okay? So that, and what we mean by interfere is that the waves that come out of the cell phone and the radio waves that we use to pick up our television signals actually do interfere with each other, okay? And it's not good interference. It's not a good thing that happens. Now, the definition of interference, if we look on the board, is that it's the phenomenon in which two waves superimpose. Superimpose simply means they meet each other and they cross over to form a resultant wave of greater or lower amplitude. Okay, so we have two waves. Here we are going to talk specifically about transverse waves. Okay, we're not going to worry too much about longitudinal waves. Transverse waves that now meet. So the first situation we can get is this. Now, I realize it's actually maybe a little difficult to see what's happened, so I'm going to draw over it so you can see. Now, the situation we have here is I have wave A over here, which is coming along, has a crest, and there it goes. Okay, so this is wave A, and it's moving in that direction. At the same time, we have wave B coming from this direction. Here's a crest, and it's going this way. Now, these two waves are moving towards each other, and their crests are coming together. What happens is we get a resultant, and this is just for a brief moment, okay? It's in green. These two crests reinforce each other, and we get a nice big crest. So that's A plus B. They reinforce, they construct something new, they make something bigger, okay? Then what happens is the wave, they come along, the crests meet, they increase in size, and then they go past each other, and the waves carry on as if they never met. So here's A, which keeps going towards the right, and here's B, which keeps going towards the left, okay? So constructive interference is when two waves meet and they meet in phase, okay? So that means that I have two crests coming together or I have two troughs coming together and they are in phase. So the crests meet at exactly the right time, increase the amplitude, make it bigger, and then move on, okay? It doesn't change the frequency of the waves and it doesn't change the wavelength of the waves, okay? So it does not affect any of that to do with the waves. It simply changes the amplitude for a small moment in time, okay? That's constructive interference. Now, what happens when we have destructive interference? Well, hopefully you guys are going, well, if constructive means they get bigger, destructive must mean they get smaller, which is exactly what it is, okay? So once again, we have our two waves. So here's A, I'm going to make it blue this time, comes along. B comes along. Now watch what's happening. A is a crest, B is a trough. Now those two are coming together, and when they meet, the bottom and the top cancel each other out. And the resultant is this. No wave, okay? No amplitude. Now, we only get zero amplitude if the crest and the trough are exactly the same size, okay? So, in other words, if my crest is 3 centimeters, then my trough is 3 centimeters, okay? That's the only way we can get zero. Otherwise, if, say, my crest is 3 and my trough is 2, I get a little crest of 1. Okay, I'm hoping you guys have sort of seen what I'm saying. Then what happens is afterwards, well, B carries on as if it never met A, and A carries on as if it never met B. Okay, so for that brief moment in time, they cancel each other out, and then they move on. Okay, as if they would never been together, as if they'd never met. The waves are quite happy. We don't lose any energy, we don't lose any frequency, we don't change frequency, wavelength, nothing. Okay, so constructive interference, when two waves superimpose, they meet, and we have them in phase. So a crest meets a crest or a trough meets a trough. Destructive interference is when two waves meet, they're out of phase. It's also a good way to describe it. They're out of phase, okay? And a crest meets a trough and they cancel out their amplitude, okay? So that gets us to a question. Now this is an interesting pattern for you guys, okay? So what we have here is I have two water waves, okay, that are being produced at the same time. Two water waves, for example, here's my source 1, it's the purple, and source 2, which is also purple, okay? And they create waves. Now, in order for us to describe or draw the waves, we draw them as wave fronts, which we'll do again a little bit later, which means these lines represent either a crest or a trough. We've decided that the thick lines, the thick dark lines, so these slightly thicker lines, those represent crests, okay? So wherever I see a thick line, that's a crest. Now, this wave follows the same pattern any other wave does. Crest, trough, crest, trough, crest, trough, okay? These two waves are moving out from the same place, and they're circular waves. So, for example, they're made from like a dripping tap, okay? A tap drip, two taps dripping, like the hot and cold water dripping at the same time, okay? Which is annoying, but let's not go there. Two circular waves are made. These waves are moving forward, and they keep being made at a constant rate, so they have a constant frequency. As a result, as the waves move out from each other, parts of the wave now superimpose. Okay, so there's superposition. They interfere. And in fact, they now ask you what type of interference occurs at 3 different points. Point A is over here. Let me just mark it over here. It's one of those blue dots. So now we say to ourselves, okay, constructive interference happens when a crest meets a crest or a trough meets a trough. Destructive when a crest meets a trough. Let's see what happens, okay? So point A over here, we have a crest meeting a crest. So at point A, we have constructive interference happening. your reason, because a crest is meeting a crest. Okay, two crests are overlapping. We all okay with that? Point B is in the middle here. It's that open space. It's a little difficult to say what's happening there. It's neither, because it probably is a mixture of constructive and destructive interference, which really means it's a little bit of constructive interference, but we can't say for definite, because it's between, you have between a crest and a trough, between a crest and a trough. It's like two rest positions meeting. That's, can't really say it's constructive interference either, okay? Over here though, and they mean point C is actually that point over there. Okay, now if we look at that point, we go, okay, hang on, wait. Thick line, thin line. Crest meeting trough. They're opposite. One's going up, one's coming down. Destructive interference. Okay? Crest is meeting a trough. You guys okay with that? Just as a little bit of extra for you, where we have, so these blue points, which all represent constructive interference, these are known as antinodes. Okay? And if I join a whole bunch together, it becomes an antinodal line. These beige points on my diagram, they actually represent points of destructive interference because I have a trough meeting a crest. And these are known as nodes. Okay? They're known as nodes, which means if we draw a whole bunch of them together, we get a nodal line. Okay? And in fact, the way I remember whether they're antinodes or nodes is I go to the opposite to what I think. Okay? Because constructive interference for me is something positive, it's constructive, it's good, and yet it's called an antinode. So it's the opposite to what I would expect. Okay? I would have expected it to be called a node, but it's not. Okay? So, after all of that, I'm going to quickly blow your mind for a few minutes, and then we'll go to a break. So
Okay,
give me a couple more minutes.
Yeah.
We now need to get into what's known as Huygens principle. But before we even do that, we need to define what a wave front is. Because we talk about it, and we draw these lines, and we often talk about a wave front in the sea and all of that sort of thing, but we go, what does that actually mean? Well, a wave front, if we look at our definition, is an imaginary line, okay? It's an imaginary line joining all the points in a wave that are in phase. Okay, now I recently had this discussion with my grade 12s because it's a section I'm busy teaching with them. I haven't got there with my 11s. And they were all like, no, really? What does that mean? Well, if I draw a little diagram at the top here, and we say, okay, let's consider a whole bunch of circular waves moving together, okay? So we have a whole bunch of little waves like this. There's my circular waves. Now, the green part represents a crest, for example. Instead of drawing all these little waves all the time, because they move together as a whole, I can rather go, okay, well, let me rather take one line and join all these crests together. That becomes my wave front. Now, whenever I describe the wave, whenever I look at its shape, whenever I look at what's happening, I use the wave front rather, because that's just easier to work with than to continue to draw all these little circles, and you'll see in a second it can get very, very messy. Okay? Now, why is this important? Because of Huygens' principle, who says all points on a wave front act like a source. Okay? Part one. Each of these point sources, which we call secondary sources, produces a small circular wave which moves forward with the same speed as the waves. Okay? The new wave front is obtained by drawing a tangent, drawing a line across all of them, to all the new little wave fronts. Now, please, I can hear some of you going, oh, do I have to learn that whole statement? Yes. Okay, end of discussion. My kids don't like that idea. All right, so what does that mean? So if we look at my diagram, it's not as clear as I would have liked, but that's okay. this is what it's saying. Here's my original wavefront over here, this part, okay? Wavefront. On that wavefront, we can pretend that there's a whole bunch of tiny little sources. So here's a source, there's, no, it would be, yeah, no, we can have one over there and over here. And it's like having millions or hundreds of little taps that, if this was a water wave, dripping onto that along in a line, okay? As a result, each of those little sources create new waves here. Okay, so they each create, I'm not doing so well with going over my picture, but just pretend. Okay, so they create a whole bunch of new round waves, which we can then join together with a secondary wavefront over here. Then we can say, well, on this wavefront, there's a whole bunch of new secondary sources which create a new set of round waves which we can then join together, okay? Whether we're dealing with a straight wave like this one or whether it is circular like in my second example, okay? This diagram is much clearer in the notes if you download them from Facebook or the website, okay? If it's a circle, so the original wave is a circle, then my point sources just mean that I get this shape. They still go around in a circle. Okay, it's just circular now. So they take this, they don't change the shape of the original wavefront unless, which is what we're going to do after the break, we go through a barrier, okay? They keep the original and they just keep moving forward and they keep moving out, okay? So what am I saying? Wavefront, this is Huygens principle in hopefully easier English. Wavefront, on the wavefront, whole bunch of new little sources of waves which create tiny little round wavelets around it, okay? Then if we draw a line across the top of those waves, the circles like a tangent, which is what this line is, we create the new wavefront. Then we have a whole bunch of little sources, creates new bunches of little waves, and then we draw a line across the top of that, okay? Whether it's straight or curved, it's the same thing. Huygens principle, very important for explaining diffraction, okay? And I think, Megan,
Yeah,
it's a good place for a break.
little bit.
Yeah, just a short
Okay,
one.
just a little break. Okay, guys, I hope you guys are understanding. I can see that you guys have some questions, so I'll go through them with Tracy in our ad break. But for now, quickly jump up and down, run around the house, come back, and we'll learn more about Huygens, however you pronounce it, we don't know, this principle. So we'll see you after the break. Okay, catch you later. Welcome back, grade 11s. We're here doing physical sciences diffraction. So Tracy and I are going to do something really, really cool later. But right now, she's going to explain more about Huygens principle. No one knows how to explain it, so we're just going to leave it. And we'll get right back into it. Let's go, Tracy.
Thank you, Megan. Yeah, you're probably pronouncing his name
Huygens.
better than me, because it is,
My physical
Austrian
science
and-
teacher he's like Huygens.
yes,
So-
and John,
Yeah,
content
Huygens.
manager, will
So
tell me that I'm pronouncing it
Huygens.
wrong. But it's okay. You know what? It's one of those things you realize I teach science for a reason and not English, okay? And my kids will know the same with the reason why I teach science and not art.
Yeah.
In fact, they laughed. Another story. Anyway, so I want to show you some diffraction, okay? Because I want you to see it, and then we're going to talk about what is actually happening, okay? Now, we're just waiting for it to have a bit of a moment. Hopefully it's going to download. We all know about PhET. We love PhET, okay, which is phet.colorado.edu.
They can download it on the notes. There's a link. 'Cause I know
There's
they're
their
gonna
link to
ask
PhET.
for it.
Brilliant. We love PhET. PhET has got the most awesome simulations. So we're just seeing at the moment whether it wants to let me run it. So we're just going to try again in a second, because it really is not liking me today. Okay, we'll try again. It looks like it's going to. But before we get there, okay, because we're going to do a whole bunch of stuff. Now, what I need from Megan
Yes.
is she's going to be my little bit of a guinea pig. Now, please, you've got to be very careful with what we're going to do now, because what I'm actually going to show you is diffraction using a laser. Now, I have the yellow sheet of paper simply because, and we're going to focus in on it just now, because it's really nice for us to see. And I have a really bright laser, which I'm not going to shine in Megan's eyes, because that's not good, okay?
No, bad.
You don't do that. Yeah, okay, anyway. So, and what I have here is a mirror, okay? And it just happens to be a mirror, but it's no real reason. And I'm not sure if the camera's going to be able to pick it up. We'll do it this side. But there's been a very thin slit cut taken off from the back of the mirror, okay? Because this grey stuff is actually what makes us a mirror, okay? So this very thin strip has been taken out. Now, the reason why we're doing that is because I want what is known as a diffraction grating. I want a single slit. Now, we use a laser because a laser gives me a very coherent light source, okay? Gives me a coherent light source which is in phase. And it gives me a light source of a single color. And we try to do it through this with a bright light, but unfortunately, the source we have has got two lights and it just does all sorts of weird things. If you do this through a single slit with a single light source, and it's white light, normal white, clear light, it actually diffracts into the colors of the spectrum. It's very, very pretty. It looks like a rainbow, okay? But we're not going to do that because we're going to look at what happens when I use it with red light, okay? So, Megan.
Yes.
I need your help now.
Okay.
Oh, okay, I don't think it's actually going to, let's try again. So, you need to face me a little bit. So we're going to do here.
So I stand with John.
No, that's cool.
Just like that.
Our director will soon tell us if we've got it wrong. Okay, so, not in your face. Sorry, there we go. So, no, there we go. Hopefully, this takes quite a bit of coord, which we know I don't really have. So there we go. There, not in your eyes, sorry, Megan. There, there we go, look at that. So, if you look carefully, if I can I'm shaking, how bad is that?
It's okay.
Yeah, I know, I'm going to have to.
Just come closer, yeah.
There we go. So, if our wonderful, can you see that in the camera, I hope? Struggling, let's move. There we go. There we go. Now, if you look carefully, sorry, it's just because I'm shaking so badly, it's frightening. Anyway, so if you look carefully at that, I'm not going to be able to move my hands, so let's just pretend. There's a bright light in the middle. There is, I promise. There we go. Bright light in the middle. Let's put it there. There we go. Sorry, Mr. Director. I know you hate me right now. Yeah. Anyway, there we go. Oh, jeez. Right now, everyone's having a good laugh. It's important to laugh at science. So, bright light in the middle, and then there's dark bands on the sides if you look at it. And I'm just going to stand still for 2 seconds, because when I talk, it goes all funny. There we go. Brilliant. Okay. So, apparently you can see that really nicely, which is very cool. Now, if you look carefully, if I don't move my hand. Yeah! Anyway, apparently swearing on TV is bad. So, yes, a little. So.
Must I swap with you?
No, I'm good. I'm good. Okay. It's more fun this way.
Okay, cool.
Don't you know this is why we become science teachers, to embarrass ourselves completely?
Okay.
Yeah. So, bright part in the middle, which I know you've seen, and then on the outside, you see that it gets dark. There's like dark bands. Thank you.
Cool.
And we're going to try once more to get this to work for me. But I'm thinking this is just not going to, okay. We're going to try once more to get the simulation to work. If not, we're just going to have to move on without it, unfortunately. Yeah, it doesn't like me today. I'm telling you, it's all a conspiracy. But that's besides the point. You know, it's called live TV. Anyway, so if I can't get it to go and we can't get it to run, guys, please go and visit this website and find the wave interference, because it's got a lot of really good stuff in it. And unfortunately, we'll get it, hopefully we'll get to see it. The light is great. It shows it really, really well, shows the patterns really well. And you can start to play with the slits and how wide they are and that sort of thing, which is what I really wanted to show you. But I have a feeling it's just not going to play with me today. Now, the reason why I wanted it is because the slit I used for the laser now is a very thin slit and of a specific width. And I don't have the ability, because of the way we're doing it, I don't have the ability to make the slit wider or thinner. And depending on how wide it is, that's going to determine how big that middle part was. Because if you remember, if you think back to what you saw in the yellow card, the middle part was very, very bright. And then as it goes across the sides, it gets lighter and lighter and lighter, and then there's these dark strips in the middle, okay? Now, what is actually happening is as we're going across, we're getting a certain type of interference pattern, okay? And I think I'm going to give this up as a bad joke, and we'll try again just now. So, we'll come back to that. Now, when we look at water waves, now this is actually a great picture. And in fact, if you go into Google Earth and you go anywhere along our coast where we've got nice beaches and jetties and stuff, you see this really nicely. Now, this picture is great because this shows a water wave. It shows a very clear wave front, which is the white part, comes to a barrier, and look what happens to the wave. It bends, okay? Now you're saying to yourself, hang on, wait. But Tracy, you just did an experiment with light, which went through a slit, but it didn't bend, per se. Well, think about what was happening, okay? I shone a very thin beam of light, okay? It's thin, thin, thin. It's a laser, okay? In fact, I think if I put it onto the screen, you can see very briefly, I'm sure my director, you see it's very thin. Thin, thin laser light, okay? That tiny little pinpoint light gave us a wide pattern, okay? And in fact, the pattern was probably about 5 centimeters wide. So now you've got to say to yourself, hang on, what do we know about light? Light travels in straight lines, okay? So how did I make this tiny little pinprick get wider? By putting it through the slit. That is diffraction, because what's happening, okay, is the wave is bending, okay? So this wave is now spreading out as it goes out, okay? This is a water wave. Water waves are transverse waves. Light waves are transverse waves. If it can happen with water, it can happen with light. Okay, so be careful here, all right? Now, let's try and explain it. And this is where Huygens' principle is very, very important. I'm going to go through this very slowly, okay? We have over here my original wave front. Whatever that wave front may be, okay? Light, water, whatever, okay? The wave moves, gets to the barrier. This is my barrier, which was the other side of the mirror of the slit, okay? Then it gets to the slit. Part of the wave gets to the slit, moves to the front of the slit, okay? Some of it will get reflected. We're okay with that. Gets to the slit, and now what happens is, remember, we've got a new wave front over here. On that wave front, there are lots of little secondary sources. Okay, Huygens' principle. Secondary sources. Those secondary sources now create new waves, which move out in circles. Okay, so I just want to make this a little thinner. All right, I want to go there. Just, okay, it's just a bit easier. So now this creates a new wave front, a new wave front, a new wave front, a new wave front, new wave front, new wave front, new wave front, okay? Not exactly in line with the source, but it's okay. But this is circular. This circular wave front now gets bigger and goes here. It's starting to bend. Gets bigger and comes here. Gets bigger, goes here. And it moves out. What has happened? This straight wave, this little point over here, has created a wave that now is going upwards. It's changing direction, okay? Here, this one at the bottom, if we create the wave that just gets bigger and bigger, and this is actually, this diagram is quite clear in the notes. Oh wait, look at that. It fills up all the space. So now we've got this new wave front that has waves that are traveling there and there. We've bent the wave around the barrier. Okay, so we've bent it. So that's exactly what happens with light. Whether it's a thin light, thick light, whatever it is, when it gets to a barrier like this, it can bend around the barrier because of the new sources, which is why Huygens' principle is so important to us. Because remember, when if we have to draw the same for all of them, it's just going to get messy. We join all the wavefronts together, okay? And that creates the new wavefront, which then bends because of the slit. How much it bends depends on a couple of things, which we will discuss in a second, okay? So how much it bends is set. So it's not an arbitrary thing. It's not a case of, oh, well, it feels like today when it goes to the splits, it's going to bend a little bit, and then tomorrow it's going to bend a little bit less. You know, it's not like us. There's set rules to how much it's going to bend and what the maximum it can bend and the minimum, okay? Obviously, the minimum means it doesn't bend at all, so pretty much it's not going through a slit. But as soon as it goes through any sort of slit, barrier, past a barrier, okay, it bends. Might only bend a little bit. This is actually not a lot of diffraction on this particular diagram. Might bend a lot. Why does it bend? And I know I'm repeating myself, but it's really, really important because wavefront, the wavefront has a whole bunch of point sources in it, okay, which are our secondary sources. Those secondary sources create new wavefronts, which are circular. If we then join all our wavefronts together like Huygens' principle says to us we get a new wavefront which shows how it bends, okay? And that's how I can take a thin point laser and create a wide pattern which is about 5 centimeters long, okay? And I think, no, let's do this quickly and then we'll take a break. So I said to you how much it bends depends on the slit, okay? So it's really easy to remember. If it's a wide opening, little bending. Wide opening, very little diffraction. Small opening, lots of diffraction, okay? So the smaller the opening, the more it bends, okay? And in fact, that's what's happening with the laser, is the laser is going through a very tiny little slit, which then creates this big pattern around it, okay? Big pattern around it, very important. Lots of bending, okay? I'm hoping we're getting this. Wide slit, very little bending, very little diffraction. Small slit, lots of bending, lots of diffraction, okay? And in fact, to get this maximum diffraction, this slit cannot be smaller than the wavelength. As soon as it's smaller than the wavelength, will be reflected. As soon as it's bigger than the wavelength, we get less than maximum. Maximum diffraction happens when the slit width is the same length as the wavelength of the wave that's going towards the barrier. Okay. I think, Megan,
Yes?
that's a good place for a break.
You're right. You're right.
Yeah.
Okay. Well, I'm posting right now about Huygens. We're just going to go with its principle. And I hope you guys take a look and tell me what you think. I'll ask Tracy now in the ad break to answer any of your questions, as well as ask her about where I can get the link for the simulation that's just giving us a little bit of technical difficulties. So quickly go for a little break and we'll be right back afterwards, okay? And we're back, grade 11s, to another live show of Physical Sciences. You're here with me, Megs, and Tracy, and we're going through all you need to know about diffraction of waves and light and how it works and Huygens' principle. So I quickly asked her about the simulation, and you can download it at the notes, which is mindset.co.za/learn extra with an X. So please, let's just get back into this, and then we'll answer all your questions at the end, okay?
So I have to just say, I'm very distracted by Megan's nails.
Oh, my leopard print.
Yes, on one nail only. I think it's quite hysterical. But that's besides the point. I'm now done. Okay. So Megan's doing a great job, actually, because she's also putting up onto the Facebook page the diagrams we've been using. So that's also great, because I know they didn't come out as well as I would have liked, but that really is my fault. Now, before the break, we spoke about how the slit width determines the degree of diffraction, okay? And in nice mathematical terms, we can pretty much say, if we say the slit width is D, okay, my slit width is inversely proportional to the amount of diffraction, okay? very bad way of writing it, but it's okay. You get the point. Now, so in other words, how much it bends. That's even hideous. The other thing that determines how much it's going to diffract is the wavelength of the wave. Now, we used a red laser, and they're the most common ones we get, but if I'd used a green laser, I would have got not a completely different pattern, I would have got a different size pattern, okay? Because wavelength, all right? So if I have the same size slit, but I increase the wavelength, I increase diffraction. So bigger wavelengths give me a bigger diffraction, okay, from the same slit. Small wavelengths give me a small diffraction, okay? And in fact, if we look on the spectrum, green has a smaller wavelength. No, has a longer wavelength than red, so it will give me a greater diffraction, okay? I've got to remember those. Now, let's get the nitty-gritty of why did we see that bright band in the middle and then the dark bands on the sides, okay? Because I'm hoping you all understand why the light could spread out into a pattern, but now we're going, well, if the wave is bending, why isn't it just one big red stripe? Where do those black things come from? So, what we have here, and I know Megan's busy putting it on the page as well, is the diagram that's very similar, okay? Here we have the blue is the barrier. We have my wave, which is coming through, and we have different points. Don't worry about the A, B, C, D, and E, okay? Then we have our wave front over here, okay? That wave front has my points on it. And now what we're going to do is we're going to make it into color so you can see this, okay? Because remember, the wave front, I want to make it quite thin again. So this first part of the wave front here, okay, it didn't go nice and thin, but let's just pretend let's do that, okay? That's my crest. So each of them make a crest to start off with, okay? Then it'll make a trough, then we'll make a crest. Okay, so there will be a crest, and there will be a crest. Okay, let's change, and then let's do the trough. Ooh, there we go. In the middle. Okay, and then there's another one. Okay, now, if we look at this, and we go, hang on, there's a pattern happening here, because I have crests and troughs, crests and troughs, crests and troughs. As the wave, now remember my wave front will bend, let's do it in purple, the whole wave front, if I had to draw it, would bend like this, eventually, around here, okay? I'm not worried about that. What I'm worried about is, as I look at my picture, and I go, hang on, wait. Over here, a crest is meeting a trough. What happens when a crest meets a trough? Destructive interference. Now, this is, say, a laser light, which is coherent, which means completely in phase. So that means when this crest meets this trough, they are 100% the opposite of each other. They cancel each other out. If the wave gets cancelled out, there's no light. Okay? There are other places where crest meets a crest. Increase. Constructive interference increases the amplitude, becomes much brighter, okay, which is why that middle spot was so bright. Constructive interference, we get a bright spot, okay? And in fact, if we look at the way this is being drawn, and you can sort of see it from here, over here we get a line that shows destructive interference, results in a dark spot on my screen, okay? The middle part here, and this is actually the inverse of what we're doing, that middle spot is actually supposed to be a bright spot because of the way we put the diagram in, okay? So this would be red or purple or whatever the color might be. That is where we have the maximum amount of constructive interference, and it comes from the middle, okay? This graph that's shown over here, that looks a little like a big squiggly line, okay, or octopus gone wrong. That is showing the intensity or the brightness of the light. The bigger the line is, the more intense the light is. So this middle band is extremely bright, highest intensity, okay? When it gets to these points, 0, nothing, black, gone, no intensity, no light. The middle band, constructive interference, because we have a coherent source. Constructive interference, bright band, lots of light, okay? The dark bands are because all their miniature wavelengths, destructive interference is happening, okay? That destructive interference results in no light being there, okay? As we move further and further away, the light gets less and less bright. It starts to get dimmer. But that's also because of the bending, okay? And my earpiece is having a moment today. Sorry, okay? Because the light is bending. So there's a limit to how far that light can bend. It's not going to go on forever, okay? And it gets less and less intense because it gets less and less amplitude. Change the color of the light, same pattern, we change the size of the pattern. That's all. So what's happening? Because of Huygens' principle, we have all the secondary wavelets. Those secondary wavelets create our new wavefront, but each of those little secondary waves interfere with each other. Constructive interference results in the light, in the bright white, or the bright red, or whatever the case may be, the bright parts in the middle. Destructive interference results in the black parts. Okay? I think I have a question, and I'm pretty sure there's some on line.
There's a
okay?
lot. Yeah.
So let's quickly do the question I had prepared.
Okay.
Said monochromatic blue light is, monochromatic just means light of a single color, okay, single frequency, is shown through a very narrow single slit, like we did with my mirror. When a screen is placed a sufficient distance away, a pattern is observed. Now it says, describe the pattern that is observed. Describe, not draw. Describe means we will get, what do we see? A bright blue central band, okay? Why is it blue? Because it's blue light. Bright blue central band with alternating dark and blue bands on either side of it. Simple as that. Central bright blue band with alternating dark and bright blue, or blue bands on either side. Description, okay? Hopefully, I know I won't really do this, but you never know, we could ask you to draw the picture as well, which then means if we had to draw it, okay, is I would expect you to go, well, there's my blue band, and you would tell me that that's your blue band in the middle. Then you'd have a dark band. Okay, so we color it in like we do in primary school. Then we have a bright band, then we have a dark band, then we have a bright band, then we have a dark band. And this would probably be enough. Okay, just so that your teacher would have an idea of what you're doing. Okay, now, part B. Give the name of the phenomenon and define this phenomenon. What they're saying to you is, what is this? This is diffraction. Okay? This is diffraction. How would we define diffraction? It's the bending of a wave around a barrier. Okay? Bending of a wave around a barrier. Name and state. This is the one you're dreading. The principle that can be used. Sure, my English is terrible. Which can be used to explain this phenomenon. Huygens principle. And that's that long thing where we say, well, along any wavefront, we have a set of secondary wave sources. These secondary wave sources create secondary wavelets, which then create another wavefront when a tangent is drawn across all the points in phase. Basically. It's one of those things, you're just going to have to learn it. I'm sorry, guys. And then, I like this one. Explain the bright bands observed. Bit of a difficult question with the way I've asked it, because I don't give you a mark allocation. If it's, say, worth 2 marks, literally all your teacher wants is the bright bands are observed because that is where constructive interference happens. If we're wanting more than this, we'd have to give you a bigger mark allocation. So they might be wanting you to go, well, along the wavefront, we have the secondary wavelets, which then interfere with each other, and where the constructive interference happens, we get the bright band in the middle, okay, or on the sides, either way, okay. This is all qualitative grade 11s. Next year, you're going to have to do calculations based with that, but luckily for you, not this year, okay. So it's all about the description and about what you see, okay. So, Megan.
Yeah.
Do you have questions for me?
Yes. Denise says, why is it that when you switch on a torch, so switch it on, and you put a pencil in front of it, that the torch, it appears much bigger than it actually is?
The pencil?
Yeah.
Okay.
Well.
I'm not sure I've ever seen that, Sweet Pea.
Yeah. Me neither.
I think I think it depends on your point of view, and I think it's a little bit maybe what you're thinking about, like when you drive at night, and I'm not sure how many of you will be driving yet, but I know for me, and I wear glasses, so it actually makes it worse. I don't particularly like street lamps and headlights and stuff at night because on your windshield actually eventually gets scratched, and so are the lenses of my glasses, okay? And in fact, I have this problem a little bit now with the lights in the studio, but that's okay, you get used to it. And because your windscreen is like cracked, okay, it causes, because remember, light it is straight, it's not fuzzy, but when you look at a light or like a headlight through your windscreen, it's almost like the light gets a halo around it. That is that's because of diffraction. And in fact, when you wear glasses, it makes it worse because, and that's the whole thing with night vision glasses and the like the yellow tint ones that were out for a while, is to try get rid of that, okay? Is to help make it clearer. Now, I think maybe what you're thinking is with a pencil and a torch is you've seen that fuzziness around it, which might mean you need to get your eyes tested. Because it shouldn't look big unless you put it in a glass.
Yeah.
I don't know. That was just interesting.
Yeah,
I might have to see context. Yes.
But anyway, Luwazi says, what if the wavefront is equal to the slit?
If you mean the wavelength,
I think
yeah. When the wavelength is equal to the width of the slit, we get maximum diffraction, okay? So that's when we get this nice pattern here, where it is very round. Okay, so it gives you a maximum curve when it's equal to the wavelength, okay? And if that's the maximum you can get. If this slit gets smaller than the wavelength, it's just going to bounce off, it won't even go through.
Yeah.
Okay, so you can't have that. Yeah.
Okay, but the other ones are, I don't know if you're...
Okay, well, we've got a couple more minutes, let's try.
It says, Michael asks, Tracy, help me. Light of a single frequency passes through a single slit.
Yes.
The first minimum, I can't say that word,
minimum.
I'm sorry, is observed at a point P on the screen. Point O,
okay,
yes, it's going hectic. Point O, the middle point of the central band. The distance OP is 2.5 centimeters.
Okay,
you see what I mean?
This is the grade 12.
Yeah.
Okay, this is the calculation, all right? Now, something I actually didn't mention. The minimum, which is a term I should have actually put in here, thank you, Michael, is where we get a dark spot, okay? So let me go back to that diagram because it just disappeared, okay? So your minimum over here, no, that's a max. Sorry. The white part on mine is a minimum. The minimum is a dark spot. It's the name we give to it, okay? Now, I think Michael's probably in grade 12, and I'm not sure if they've done that yet, but that's a whole calculation because we don't do the sine equation. Now, Michael, just as a bit of a help, when you need to look at the distance, you would need to use your diffraction calculation with sine in it, and then do a right angle triangle and use tan along the way, okay? That's as far as I'm going to be able to go with you. But the dark spot is called a minimum. And the first dark band is the first minimum, second dark band, second minimum, third minimum, etc. Okay, and generally we only work with the first, but in grade 11 you don't need to do calculations.
Okay.
So Michael, if your teacher, if you are in grade 11 and your teacher is doing calculations with you, I think that's impressive because she's actually helping you for next year. So don't stress too much.
Yeah, always a good thing to start early.
Always.
Anyway.
Yeah.
But yeah, that's our show today, grade 11s. Can you believe it? We actually got through the whole section of diffraction. I'm so glad Tracy and I have been with you. It's been a really, really great show. Tracy, do you want to finish it off?
Oh, Okay, sorry. I was about to just close off the
just
computer and
leave
go.
it,
Guys, keep studying. I know this is a difficult section. Learn Huygens principle. Make sure you can quote it. Make sure you can understand the whole thing with the wavefronts and how it bends, and be able to describe the pattern. Okay, and talk to your grade 12 friends, guys. They're doing the same work at the moment. So you can help each other. They've just got to do some calculations, which we'll do next year. So anyway.
Thank you, guys. Thank you for watching our show. And that's it from me and Tracy. Have a great, great, great day.